what extent one should include such data at larger Q-squared, and up to which Q-squared one should include.
Yeah.
That's Are there more questions on this first lecture?
Yeah. What is the experiment that you performed for the new EP lamp shift thing?
For the lamp shift experiment, so in the ordinary hydrogen, this was the experiment I've shown you. There will be two actually, but the one I've shown you is in York University in Canada. So, and there's one also in Garching going on, I think, in Munich. So just before I came here, my laptop broke down. So just last week, I'm sorry. So I had to use a spare laptop, and this may be related to this. Some of these fonts are not coming out as they should come out. Okay, so 10 seconds out here. Okay, this looks better. Okay, so sorry for the interruptions. So it should be fine now. So let's go through these electron scattering experiments in some detail. So I showed you last time to measure charge distributions in systems such as a nucleon. One is typically scattering an electron with exchange of one photon from such a target. And we have seen for a spin 1/2 target, so the structure of this target is parameterized by two form factors, which is the so-called Dirac and Pauli form factor. And in experiments, one often uses combinations, which are the sum, which is magnetic form factor, and the difference with the factor Q²/4m², which is the electric form factor. And in an elastic electron scattering experiment, so these form factors, which only depend on this virtuality Q², so which is basically the virtuality, the probing scale of this photon, they depend also on the beam energy of the electron, or equivalently, one is often using a parameter which is the virtual photon polarization parameter, which is epsilon, which is given here by a quantity in terms of the scattering angle, so which is varying between 0 and 1. So if one has forward scattering, so when this electron is going in the same direction as the initial electron, this is equal to 1. If one has backward angle scattering, so when this scatters at 180 degree, this is 0. So basically it's just a kinematical variable. And then the cross-section for this process is proportional, so up to a flux factor, which one can calculate, is proportional to the square of the magnetic form factor plus the square of the electric form factor, with a prefactor which is dependent on this epsilon divided by this Q²/4m². So it's a simple formula which allows to separate the electric and magnetic form factors. And this separation is shown here. So typically what one is doing is at a fixed value of Q², one is plotting the data for the cross-section as a function of this kinematical parameter epsilon. So one can vary this epsilon, for instance, by taking measurements at different values of the scattering angle, and one should see a linear dependence. So this is just a linear dependence at a fixed value of Q². And from the value at epsilon 0, one extracts the magnetic form factor, and from the slope, one extracts the electric form factor squared divided by Q². So this is well-known technique, which is known as the Rosenbluth separation technique. And so the most recent data for these form factors, so the electric form factor and the magnetic form factor, and thus the ratio of electric to magnetic form factor are shown here. So these form factors, they typically behave like dipoles, so 1/q⁴ at larger Q². So if one takes out this behavior, one has a variation which is relatively smooth, but which shows the deviation from 1 is the non-trivial dependence in these form factors. And one can see that the new measurements is this blue band is very precise at very low Q². So these are the measurements here which are being used to extract the radius, electric radius and magnetic radius, respectively. Now, a few years, 10 years ago roughly, so one has followed up on a proposal which existed already since 1974, is to measure these form factors not with unpolarized electrons, but with polarized electron beam, and by measuring the polarization of the recoiling nucleon. So if we look at this here in the scattering plane, so you have an electron which comes in, which has polarization either along or against this direction, scatters at some angle, exchanges the virtual photon, and the proton is scattered. And now this outgoing proton the polarization is measured, and this is done by scattering this proton of a nuclear system, such as carbon, for instance, and depending if the proton spin is pointing in one direction or another, it will scatter in one or the other direction of this nuclear target. So this is recoil polarization. And one can measure the component of the spin along the direction of motion or perpendicular to the direction of motion in the plane. The quantity which is normal to the plane is a quantity which is exactly 0 in the one photon exchange approximation. So there are only two components, the two polarization components in the plane, which are called PL, which is longitudinal, along the direction of motion, and PT is transverse, perpendicular to the direction of motion. Now, the interesting thing is that these two components, if one does the calculation of this diagram, up to a kinematical factor, are proportional for the sideways or transverse component to the product of the electric and magnetic form factors, and for the longitudinal one, just to the magnetic form factor squared. And if one takes the ratio of these two, one sees up to a kinematical factor, it's exactly the ratio of electric over magnetic form factors. So one has an independent measurement, so to say, of this electric and magnetic form factor. And this has been done over the past 10 years, actually in quite some detail, in different experiments, starting here in 2000 up to 2010. So at Jefferson Lab, and what is shown here is this ratio of electric over magnetic form factor extracted in two different ways. So the green points are older data points from Stanford and also from Jefferson Lab, where this Rosenbluth method, so the unpolarized cross-section, is being used to extract electric and magnetic form factors and then plotting the ratio. So one is less sensitive to the electric form factor at larger Q-squared. So I will explain you in a moment why. But typically within the precision of these experiments, this ratio tends to be around 1. Now these measurements here, all the colored ones and the black ones, they are these measurements of polarization observables with this recoil polarization technique. And one basically sees a steady decrease of this electric form factor relative to magnetic form factor, nearly crossing 0 here at a virtuality like 8.5 GeV squared. So now this of course has puzzled people quite a lot, because they're the same observables, so they should agree within errors, and it's definitely not the case. So what it means is one has two measurements to measure this quantity, and they give rise to two different results. So I would like to show you in some detail how we understand this puzzle in electron scattering due to two photon exchange corrections, which have not been applied to these data. So before going there, let me give you a general comment, because that's also something which is of relevance for this proton radius puzzle. How well do we understand electron scattering cross-sections? And to ask oneself how well one understands it, one needs to see how well one understands radiative corrections to these cross-sections. So typically, if you measure such a cross-section in a one photon approximation, there will be correction terms, which you can label here by deltas. So basically it's a 1 plus a correction term. And this correction term are due to the fact that the Feynman diagram is not just the one photon exchange, but there can be a vertex correction here between the lepton, or self-energy correction, or there can be like a vacuum polarization correction. Or there can be a two-photon correction. Now, to give an idea how large these effects are, so I show here typical kinematics, like at 4 GeV electron beam energy and at a virtuality of 4 GeV squared. So this factor delta, so is typically for this vacuum polarization, which we have seen is the dominant correction in the ionic hydrogen, is typically a correction at the cross-section level, something like 2.3% in the case of when this is an electron loop. When this is a muon loop, it's like less than 1%. Now, besides these graphs, so one needs also to take into account the fact that electrons, being ultra-relativistic, will radiate a photon, and this radiation is called Bremsstrahlung, is needed because the diagram where, for instance, here one has a vertex correction has an infrared divergence if you calculate it, because this photon can be soft, and when you have a soft photon, you can basically cut this line here, and this means that you have a soft photon emitted from either initial or final lepton line, And so there is a theory in QED which is proven that this has to cancel exactly with infrared divergence coming from these diagrams. Now, also the proton can radiate such a photon. The proton is much more heavy, so this radiation is typically much smaller, but if one wants to be precise, it also has to be taken into account. And if one includes these vertex corrections and these radiation effects, one sees that the correction is not small actually, it's like 20%. So it's a 20% correction to the cross-section. So the data basically have to be corrected upwards due to these effects. And we know these effects, of course, because it's QED, but the question is how accurate do we know them? So we need to know them to better than 1%. And then the...
Does the result depend on the detector?
Yes. So I will show you on the next slide this, just to illustrate that. And then the graphs which typically are not calculable exactly in QED, and which are the ones which are maybe troublesome, are the ones where you have corrections on the hadron side, so either vertex corrections on the proton or two photon exchange corrections between electron and proton. And the reason why they cannot be calculated completely model independently is because, although I draw here just a nucleon line, of course there can be the whole excitation spectrum of the nucleon here. Also in this vertex correction, there's no reason why this line should be only a nucleon, so it can also be the whole excitation spectrum. So one needs independent techniques to estimate these effects. And the largest of these effects are the two photon box graphs. So there is an estimate shown here. It's typically something like nearly 3% correction. This is the Z denotes the charge of the target. So effects of order Z are coming from two photon graphs. Effects of order Z squared are coming from these graphs. So these effects here, the pure corrections on the hadron side, they're typically small, 1% or less. And the leading contribution, of course, one knows, because the leading contribution is coming from soft photons. So the only thing which is not known is when these photons are not soft. So which means when this particle here is not a nucleon anymore, but can be like a resonance or something. So these whole corrections, if you sum up everything, is typically like 20–21%. So the challenge is, if we need to know it, we want to have it with a precision below 1%. So it still means you need to know these corrections 1 relative to 20. So you need to know them with a 5% precision typically. Now, yeah, coming to your question, indeed, how does it depend on the resolution? So this is actually the state-of-the-art plot to show how well we understand this radiative tail. So if you typically do an experiment, so elastic scattering experiment, so this is here the energy where you have elastic scattering, and so it's just arbitrarily put at 0. And then if you go away from this energy, it just means this is the energy which is taken away by a photon which is radiated. And this is the so-called radiation tail. And this radiation tail, so there is a logarithmic dependence on this energy. And this depends, of course, on your detector setup and what is the resolution in your experiment. Now, typically, if you understand your experiment very well, so you know how to simulate this. You have an analytical function, actually, which depends on this resolution. You can divide your data by this function, and then you should reconstruct the constant. So whatever you want to extract, like a form factor or Python distribution, it should not depend on this radiation effect. So within, and that is shown here. So this is basically the ratio of the data to the theory which describes this radiation effect. People call this a plateau method. So what you see, this is a very expanded scale. So this is 5 per mil, and this is -5 per mil. So and this is here 1 per mil. So it just shows within 1 per mil. So this should be ideally a constant. Yeah? So you can reconstruct the constant within 1 per mil, typically. So eventually, if you go high enough, you will hit the pion threshold, and then you will start to see deviation. But within the range here where these experiments are done, one understands these resolution effects to within 1 per mil. That's okay. Now let me show you the history of these two photon corrections before and then coming to the present. So they've been estimated historically in the 1960s here by Tsai and Mo and Tsai for the first time, who calculated basically this box diagram. And they calculated this box diagram assuming there are only nucleons here in this intermediate state. And the dominant contribution, if you calculate such a diagram, are coming from the regions where this Q1 and Q2, so the photon momenta, are close to 0, so when they're soft. So because this is the case, so what they did in their calculation was to make this approximation in the numerators here and denominators here of the lepton and nucleon propagators. So this is just a way to reconstruct the infrared divergent terms. And one can, of course, improve on this, and this has been done by Maximon and Chon in 2000. So where this approximation here, where one approximates these momenta in the numerators and denominators, is only done in the numerators. So basically, technically, one has to calculate then 4-point functions. And so one has to use here on-shell form factors, so in these loop integrals. Now, a few years after that, people improved further on this by doing a full numerical calculation, not making any approximation for this momentum dependence. The only approximation is still being made is assuming this is a nucleon, and one is using here for these couplings on-shell form factors. And actually, so a similar approach has also been done within a dispersion calculation. I will come back to this. Now, of course, in order to do this in a model-independent way, one should allow here for different intermediate states, and one should also test the procedure of just putting in here these form factors. And I would like to show you in some detail, I mean, the model-independent approach to calculate these two photon exchange corrections in general. And for this, let's go back one step. Look at the scattering of electrons from nucleons without assuming anything here, just looking at this as a 4-point function. So an electron with a momentum k and a given helicity h is hitting a nucleon with a momentum p and a helicity lambda, and they scatter with momenta k prime and helicities h prime and p prime and helicity lambda prime. So how many amplitudes or helicity amplitudes you think are needed to describe this process in general? So who wants to try? Just how many helicities does an electron have? So electrons and protons are spin 1/2. So they will have 2, right? So how many will you have in total then, combinations for this? How much?
8.
8. So how do you come at 8?
2 for each.
Yes. So 8 is a good answer. But if you calculate, you already made an assumption. So you have 2 to the 4th power. So you will have 16, right? First. 2 times 2 times 2 times 2, 16. Now, indeed, so we are looking here at processes where parity is conserved. So what is parity doing with the helicity? So if you have a spatial inversion, it flips the helicity. So it means that if parity is conserved, half of these amplitudes can be discarded. So one will be at 8. So indeed. Now, 8 is still not the final answer. Why is 8 not the final answer? Because one has a process where the initial state, electron-nucleon, is equal to the final state, electron-nucleon. For such processes, there is a time reversal. So if you look backwards, the movie backwards, you can there will be the same, so the final state becomes the initial state. So let's make an assumption here. I'll just let's make the assumption here that the initial electron helicity is just positive. We can also make the assumption it's negative, but this is just equivalent. So then for the final helicity, there are two possibilities. So either plus or minus. So now let's stick for a moment with this case first. So then for the nucleons, so there is the possibility plus plus, plus minus, minus plus, minus minus. So this is all for the case where the final electron has positive helicity, and then equivalently one can do it for negative. Now, when we say time reversal, so how does it act on the helicity? So helicity is a sigma dot E. So sigma, how does it go? Sigma, okay, angular momentum is like R cross P. So how does angular momentum change? So it will change. Angular momentum changes, but the projection on the momentum does not change, because momentum also changes. So for time reversal, the helicity stays the same, right? The only thing which changes is initial and final states change. So if you look at this combination here, this is just, if you apply time reversal invariance, or you look time reversed in this process, plus minus becomes minus plus, and minus plus becomes plus minus. So if you have time reversal invariance, they are directly related. So these two amplitudes up to a phase are equal. These, nothing happens, because under time reversal, it goes to itself. So it doesn't lead to a relation. Also this one goes to itself, so no relation. So there will be, instead of 4 here, there are 3 independent ones, and 3 independent here. So from the 8 we go to 6 independent. Now, okay, 6 is the final answer. Now, the 6 can be distributed in these two categories. So the first category is when the lepton helicity is flipping. So this actually what I denoted here is the second one, from plus to minus. So is this very likely to happen? If an electron is at rest, yeah, you have 50% chance, of course. But if an electron is ultra-relativistic, or if it's basically you neglect the mass, then, so what do you know about massless particles? So helicity is conserved. Yeah? So when you have ultra-relativistic particle, the helicity of the final state is equal to the initial state. So, which means that these helicity flip processes, they are basically suppressed. They are proportional to the mass of the electron relative to, let's say, q squared, the momentum transfer. So you can neglect them for ultra-relativistic electrons. So there will be, in the end, 3 independent amplitudes. And so if you apply these discrete symmetries, which is parity and time reversal, and use the fact that electrons are here ultra-relativistic, so you get 3 independent helicity amplitudes, or equivalently, one can parameterize them as structure amplitudes. And actually this is shown by this formula. So this formula is just the Lorentz, general Lorentz structure between here the spinors of the electrons, so E bar gamma mu E. So it's a vector current on the electron side, and then N bar N on the hadron side. And the Lorentz structure here is either gamma mu or a P mu. P is the, I forgot to say that, capital P is the average of the momenta between initial and